So good morning.
Good morning.
Yeah. So today I am going to discuss two elementary bounds on codes, and after that we are going to construct Hamming code. I'll give you the construction of Hamming code. First, we'll focus on binary Hamming code. Then I will little bit talk about query Hamming code. And I will, in between, I will leave a couple of exercises for you so that you can do it on your own. And I think in assignment 3 you will find that some of these things are there in assignment 3 actually. Okay, so suppose C is our NKD code. Okay, I am focusing for binary code first. So say binary code, it's a linear code of C2 raised to power n, binary linear code, right? If the result is true even for query code, so the problem. And suppose equal some A matrix and In minus k matrix is there. This is n minus k cross n, the Petitcheck matrix of the code. Okay. Now there is a result or theorem which is known as Mds bound. Okay. So what is this Mds bound? It says that D cannot exceed n minus k plus 1. So it's a beautiful bound. That minimum distance of the code cannot exceed n minus k plus 1. What n is the dimension of the code, right? And d is the minimum Hamming distance. So how do we prove this? The proof is really simple. We know that rank of h. What is the rank of h? Can you tell me? H. Rank means maximum number of linear independent columns, whatever you want to say. So here, because of the presence of this In minus k, identity matrix of size n minus k, rank of h is n minus k. Okay. So all these rows or all these columns, basically all these columns are linearly, because of this, so all these rows are linearly independent. N minus k rows are linearly independent, right? So rank of h is n minus k. So rank of h is nothing but maximum number of linearly independent, I can say, columns, right? That's the definition of rank. Now we know that in the Petitcheck matrix H, any D of H are linearly independent. Now, since any D minus 1 columns of H are linearly independent and maximum number of linearly independent columns are n minus k, therefore D minus 1 should be less than or equal to n minus k, the maximum number, right? And in other words, D is less than or equal to n minus k plus 1. So we arrive at the bound. Okay. This is known as MDS bound, maximum distance separable. Okay. Max distance separable. Maximum distance, or in short, we call it as MDS. Okay. Now, MDS bound. Codes for which D is equal to exactly n minus k plus 1, these are known as MDS code. And examples are, there are plenty of examples, but the most popular one is Reed-Solomon code. And we will discuss about this Reed-Solomon code later on. and you can see that they have a lot of applications in QR codes. QR codes, which is very common that you use from your mobile phone. So they use read solver codes. Read solver codes are also used in many hard disk storage and so on. They are very popular. So the first bound, this is Mds bound. Now I want to describe another very important bound known as sphere packing bound. So what is this sphere packing bound? This says that a T error correcting binary code of length n and containing m code words capital M code words, total number of code words are capital M, okay, must satisfy the following relationship. Must satisfy the following. And the relationship says that capital M times capital M times 1 plus n choose 1 plus n choose 2 plus dot 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 n choose t less than or equal to 2 raised power n. This is a very nice result, and I am mentioning it first for the binary code, also explain it for query code. So how to arrive at this beautiful result? So what we are going to do, so we know that 2 raised power n is the size of the whole space. Z2 raised power n has 2 raised power n vectors, right? And code has capital M code words, right? What I'm going to do now, on each code word, if I draw a sphere of certain radius, okay, so how many code words it will have? Actually, uh, this is this total number of code words in a sphere of radius t is this quantity that we are going to see actually. Okay, so the proof involves counting total number of code words in the sphere of radius t. So suppose st of c is a sphere of radius t. All those code words x in z2 raised to power n such that distance between x comma c cannot exceed t. This is the sphere of radius t, right? Around a code word c in c. C is a part of c. Okay. What is the size? So note that if I want to know the size, total number of code words in this sphere, so this will be, I need to count how many how many vectors are there which are distance less than c. The total number of distances less than or equal to t. So possible distances are 0, 1, 2, 3 up to t, right? So how many code words are there of distance 0? Of course, there will be only one, right? Now Now we need to count how many vectors are there which are of distance at most one from C. So at most ones means, there are total n positions, and one position will differ. So I have to choose one position which will differ. So how many ways I can choose that? And choose one, right? Plus, how many code words are there which are of distance at most two? Again, since I have to make two choices, it is n choose two, and so on for n choose t. Okay. So this is the total number of code, because the possible distances are 0, 1, 2 up to t, right? So how many vectors are there which are at distance 0? How many vectors are there which are distance 1? How many vectors are there which are distance 2, and so on? How many vectors are there which are distance t from C? If we count that, that number turns out to be this. Okay. Now we know that this is when the code word is C, which is an arbitrary code word. Now this is total number of. Now we know that size of C is capital M, right? So that means total number of code words will be M times 1 plus n choose 1 plus dot 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 n choose T. Now this quantity cannot exceed total number of code words in the space, which is 2 raised power n, right? So we arrive at our beautiful result known as sphere packing bound. Okay. Now I can write down in a much better way. Since t is d minus 1 by 2, I can write it down as summation. Okay. And choose I is equal to 0 to greater than 0 d minus 1 by 2 less than or equal to 2 raised power n divided by capital M. That's another way of writing it. Okay. Or so this is for binary code. Okay. The result can be generalized in the query case. So for query code, when C is n, k, d, and query code, this is nothing but summation I is equal to 0 to greater than 0 d minus 1 by 2 and choose I times q minus 1 less than or equal to q raised to power n divided by cardinal T of C. In other words, it is q raised to power n divided by capital M, or q raised to power n divided by q raised to power k. Okay, so this is known as sphere packing. This term here comes because we need to make another choice, for the vector x. The vector x can be chosen in q minus 1 ways. Okay, so that will give you this quantity for each case. Okay, so this is known as sphere packing bound. Codes which meets these bounds with equality. So basically, so this bound is nicely written as so codes for which we have summation I is equal to 0 to d minus 1 by 2 greater than 0 and choose I q minus 1 raised to power I less than or equal to q raised to power n minus k, right? So this is our actual bound. codes for which equality holds here are known as perfect code. Perfect. It's a beautiful concept. That means what we are doing here, we are taking uh, a, we are taking linear code C, or even if you take a general, if you're taking a code C uh, in the space fq raised to power n, taking a code word in C and drawing the spheres of radius t. These spheres are disjoint, we know, right, from our previous lectures. So when these covers the whole space, the code is known as perfect code. Okay, so in this case, when it covers the whole space, in that case, equality will hold. So total number of code words in these spheres multiplied by the total number of code words is actually equal to q raised to power n, total number of code words in the space. So there are some nice examples of perfect codes. Actually, you can solve this inequality for q, n, k, and d, and you see that there are certain values that will come up. It turns out that code does not exist for all the values, but it does exist for three important results. So one of them is so when q is equal to 2, we know that there is a code known as Hamming code. So basically, I am going to describe it now. First, I will describe q is equal to 2, Hamming code. Second is Gole code. Gole code, of course, exists for q is equal to 2 and q is equal to 3. So I am going to discuss the q is equal to 2 case first. Okay, and so very trivial example is repetition code, which is also perfect code. Okay, so you know that what are the parameters of repetition code? N, 1, n, right? K is equal to 1, d is equal to n, and length is n, right? So repetition code. So I'm going to discuss Gole code, Hamming code, repetition code. So you can substitute these values here and see the equality will hold. Okay. So now we are ready to describe Hamming code. I'm going to focus on the binary case first. This was the first interesting code. Although this was discovered in 1947, this was published in 1948, but I would say the dual of this code was already known in statistics. It was discovered by Ronald Fisher, a very famous statistician, who talked about dual of this code appearing in the statistical design experiment. That so basically first time these things were known in 1942, and then later on rediscovered by Hamming for the application in error correction in 1947. And actually, because of the patent issue at AT&T Bell Labs, because Hamming was at AT&T Bell Labs, it took him some time to publish it, and it was published in 1948. Okay, so this was really a nice discovery. It's a single error correcting code. Let us see how to construct this code. So I am going to look at I will try to construct the Petitcheck matrix of the code. Okay. Okay. So let us take if I take H to be the matrix consisting of uh, It's a matrix consisting of, I can denote it by HR. R is a parameter, R rows and 2 raised to power R minus 1 columns consisting of all binary non-zero columns of length R. Okay, this is the definition of the Petitcheck matrix. All binary non-zero column length R. So you know that vectors are possible, 2 raised to power R, right? So if we exclude 0, they are 2 raised to power R minus 1 non-zero ones, right? And length is R, so it is R rows and 2 raised to power R minus 1 columns. This is known as the Petitcheck matrix. So let us construct. Let us see how to construct it. In case of R is equal to 2, H2 is okay 1 1 1 0 0 1. These are all three vectors, right? Now, one property that you can observe here, that if I take any two columns here, they are linearly independent.
Sir,
Yes,
uh, sir, how the r into 2 raised to r minus 1 is arrived? So if
because total number of, see, if you look at what we are looking at in this space, z2 raised to power r. How many vectors are possible? 2 raised to power r.
yes,
Now I am saying that all binary non-zero columns of length r. So that means non-zero. I have to avoid 0, 1. So total vectors are 2 raised to power r. 0 vectors you avoid, it will be 2 raised to power r minus 1, right?
yes,
So that's how.
yes, yes, yes,
Okay. So now, for example, in case of r is equal to 2, we see there are 4 vectors possible. You exclude 0 vector, so we are left with these 3 vectors, right? And the important property that I was mentioning here is that any two columns are here. Okay. If I take this and this, 1 1 is not multiple of 1, either 1 0 or lambda times 0 1, right? So any two columns are linearly independent. This is a property here. Now you remember there was a result if H is a Petitcheck matrix of a linear NKD code, then any D minus 1 columns are linearly independent. So there is a connection. So if we are able to show that any two columns are linearly independent, so the minimum distance of this code turns out to be 3. Because any D minus 1, two columns are linearly independent, right? If we take 3 columns, then they are dependent. For example, this plus this is first column, right? Okay. If we sum 1 0 plus 0 1, we will get 1 1. Okay. So 3 columns are dependent, but any 2 columns are linearly independent. No matter which 2 columns I take, they are not multiples of each other. So it turns out that minimum distance D turns out to be 3. If minimum distance D, what is T? How many errors it can correct? 1. So it's 1 error correcting. Okay. So this is 1 error correcting. Let us now try to construct uh, H3 from here. So we are taking R is equal to 3. That means H3. Now you observe that H3 can be written as 0 0 0, okay, 1 1 1 1, 0 1 1, 0 0 1 1, 1 0 1, 0 1 0 1. Okay, so this is our H3. So you can see that we have written all the 7 columns. In fact, you can observe another thing, that if I draw this line here and this line here, then this. So in fact, this is 0 1 1 0 1 1. Now our previous H2 written in a little different order. Actually, we can fix that order. So H3 can be written as 0 0 0 H2 1 0 0 1 1 1 H. Right? Once we know H, so where H2 is in our case now 0 1 1 1 0 1. H2 is like this. If you take H2 like this, H3 can get like this, right? So this in mind, I can write down HR